All right, 6.1 is about discrete random variables. Well, we're going to talk about random variables in general in chapter 6 and 7. Um, chapter 6 is about discrete variables, right? Discrete random variables. And so in 6.1, we're just going to introduce that concept generally. In 6.2, we'll talk specifically about the binomial distribution. And then there are other kinds of discrete variables as well. There's a variable called the Poisson distribution that your textbook covers in section 6.3. We're not going to look at that one because it doesn't really come up again in the course. So we'll just talk about the binomial distribution, but just know that there are other kinds of discrete variables other than the binomial. And in 6.1, we're going to talk about, we're just going to talk about these kinds of variables in general. So first of all, the concept of the random variable. So a random variable is a variable that has a single numerical value determined by chance for each outcome of a procedure. So to give you an example, let's use coin flipping, right? So the outcomes of flipping a coin 2 times are, well, if you flip a coin 2 times, it's possible you could get heads both times. It's possible you could get heads and then tails. It's possible you could get tails and then heads, or it's possible you could get tails 2 times. Okay. So those are the outcomes of flipping a coin. Now we turn those outcomes into a random variable by letting x be the number of times that something happens. Okay. So in this case, let's say that x is the number of times that heads occurs. Okay. Now if x is the number of times that heads occurs, then x could be 2, right? Or x could be 1, or x could be 0. Okay, x can't be more than 2 because we only flipped the coin twice, so you're not going to get heads more than twice. And it can't be less than 0. What would it even mean for you to flip coin or flip heads -1 time? Right? That doesn't make sense. So x can be 0, 1, or 2. Now the probability that x equals 0. Well, if x equals 0, right, x is the number of times that heads occurs. So if x equals 0, that means we must have flipped tails twice. And there's only one way that that can happen out of 4 possibilities, right? So the probability x equals 0 is 1/4. In other words, this isn't really anything new. It's just a slight change in perspective. We've been computing probabilities like this before. It's just that the way that we would phrase them is we would say something like, what's the probability that you would flip tails twice, right? Well, now an equivalent way to say that is to say, what's the probability that x equals 0, right? What's the probability that x equals 1? Well, that would be these two right here. We got heads once in both of those outcomes, so that would be 2 out of 4, or in other words, 1/2. And then finally, probability x equals 2. Well, that would have to be this guy right here, right? That's where we flipped heads twice, so that's 1 out of 4. Okay, so the possible values of x are 0, 1, or 2. And one thing that you'll notice is that the sum of the probabilities of all of the x's, right? When you add all these things up, you get 4 out of 4, which is 1. Okay, so that's the idea behind random variables. They just count up the number of times that something happens. Okay. A discrete random variable, well, here we're just kind of reviewing the difference between discrete and continuous, okay? Discrete variables are things that come from counting something up. Continuous variables are things that come from measuring, right? You get the values of a continuous variable by measuring something. So let's just practice. Let's refresh our memory about discrete versus continuous. So it says determine whether the random variable is discrete or continuous, and then state the values of the random variable. So part A says the number of light bulbs that go out in the next year in a room with 10 light bulbs. Would that be discrete or continuous? And I would say discrete I would say discrete, because you count that, right? You count up how many light bulbs have gone out, right? That's discrete. Now, as far as the values of the variable, x could be 0. It's possible that none of the light bulbs go out, or it's possible that all 10 of them do, right? So x could be 10, or it could be anything in between, right? Okay, so those are the possible values of the random variable x. Okay, go ahead and give the video a pause now and see if you can do parts B and C. Okay, here's my solution to part B. The number of leaves on a randomly selected oak tree is discrete. And the possible values for x, oh man, well, if the oak tree is dead, then maybe it has 0 leaves on it. And I suppose it could be in the thralls of death, right? So, or the throes of death, I mean. So maybe there's 1 leaf still on it or 2. The maximum number of leaves on an oak tree, I mean, I don't know. I think I looked this up on Google once, and it's like, it's probably safe to say that like 500,000 is maybe the maximum number of leaves you're going to get on an oak tree. Imagine being the person who had to count that up, though. Anyway, but that one's discrete, okay? And then part C, the length of time between calls to 911 is continuous. You measure that, right? You measure how much time passes. And it's continuous. X could be anything bigger than 0, right? If the world ended tomorrow, there would be no more calls to 911, right? So potentially X could be as large as you'd like. So that's that. Okay. So one of the kind of morals of this particular section is that we can change our perspective about a lot of things. Like we can look at a lot of old things that we've done in the past and rephrase them in terms of random variables. So one of the things that we do is we look at what are called probability distributions. But probability distributions, it turns out, are the same thing as probability models from chapter 5. Okay, so they're really exactly the same thing, but just stated in terms of random variables. Just like we discovered in chapter 5, probability distributions are going to follow these rules, right? All of the probabilities in the distribution have to be between 0 and 1, and the sum of the probabilities in the distribution have to equal 1, right? What does this remind you of? Right? Probability models from chapter 5. Okay. So let's just refresh our memory there. It says determine which of the following are probability distributions. Well, we have no information to go off of other than the numbers that are given to us. And here it looks like all of the numbers are between 0 and 1. And it looks like the sum of the numbers equals 1, right? 1/6 plus 1/6, right? 6 times is going to be 6/6 or 1. So this one is a probability model for sure, or a probability distribution. In part B, I think all of these are between 0 and 1, and the sum is 4, 5, 6, 7, 8, 9 ninths, so that looks good as well. Part C is not a probability distribution for sure, and the problem is this guy right here. We have a negative probability in there, and that's not possible. So, no, right? That contradicts condition 1, so the answer is no. And then part D, all of the probabilities are between 0 and 1, so that looks good. If we add them up, we get 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, 11 tenths. So this would be no, because the sum of the probabilities is not equal to 1, right? It's actually equal to 11 tenths. It's not equal to 1. Okay, so that's the idea there. Nothing new, right? We've done this kind of thing before. Here's another thing that we can do that's the same as stuff we've done in the past. It's a probability histogram. It's basically just a relative frequency histogram, okay? For example, it says, draw a probability histogram of the probability distribution to the right. Well, it should say below, right? It should say below. They're talking about this thing right here. which represents the number of DVDs a person rents from a video store during a single visit. There are no DVD stores anymore, right? This is a super outdated question. Uh, but yeah, we can do this though. We can draw a histogram of this data set. We'll just pretend that Blockbuster still exists, right? Okay, so it's just a histogram. So I'm going to give myself, well, it looks like on my y-axis are where my probabilities are going to go, right? They're where my relative frequencies are going to go. And it looks like I need to go up to 0.58. So I think really what I'll do is I'll go all the way up to 0.6. And probably I'll go up in increments of 0.05. So if I go 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. That'll do nicely, I think. And then down here, we're going to have the number of DVDs, right? Number of DVDs. So say 0 to 1, 1 to 2, 3, 4, 5. I should have just left the page number as my little tick mark. Oh well, wasted opportunity. So let's see. So one DVD was rented 6% of the time. One DVD was rented the great majority of the time. That's kind of sloppy. Anyway, 2 DVDs were rented 22% of the time, right? The probability someone rents 3 DVDs is 10%. Probability someone rents 4 is 3%. Probability someone rents 5 DVDs is 1%. Now I'll tell you something from my childhood. This was my family. We would go to, there was a video rental store in my hometown called Video Choice. Probably that's a pretty common name for video rental stores, but anyway, there was a video rental stores, and this was back in the day of VHSs, right? So I guess it doesn't apply to DVDs so much, but we would go to the Video Choice, and they had this deal where you could rent 5 movies for $5 for 5 days. So you got to keep them for 5 days. And it only cost $5 to rent 5 movies. It was awesome. So we would go in. My dad would always rent a Rocky and Bullwinkle, which if you don't know Rocky and Bullwinkle, you should look it up because it's pretty funny. Anyway, Rocky and Bullwinkle, and then we got to choose, you know, us kids got to choose some other movies and stuff. And then we just like, I mean, we didn't do this every weekend, but it was like on special occasions, you know. And then we'd go and watch movies all weekend. It was awesome. Anyway, that's that. So nothing new there. Of course, we should give this a title. We could say something like DVD rentals or something like that. Okay, so that's that. Now, here's something else that's not new, but it is a new name for something that we already know. And I don't want to spoil it for you just yet, but we'll make a connection with something else that we've seen in the past already. But so the expected value of a random variable x is denoted by this symbol right here, right? I'll read that, E of x, right? E of x, expected value. It's the value that we would expect x to take on. So for example, if x is the number of heads in an experiment where a coin is flipped twice, right? So if you flip a coin twice, how many times do you expect to get heads? Well, probably you expect to get heads 1 time, right? When you flip the coin 2 times, right? So the expected value there is 1. Now that's a pretty obvious example, but for less obvious problems, we compute E of x by taking the average of the possible values of x weighted by the probability that x takes on that value. So the formula for that is this, right? So we would say we're going to multiply each observation times the probability that the observation occurs. And then we're going to add all of those up, okay? So for example, for the coin flip example, just to verify that the expected value really is 1, for the coin flip example, we would say, well, if I flip a coin twice, And we already saw this on the first page, right? If I flip a coin twice, the possible values for x are 0, 1, and 2. In fact, maybe I'll just draw the probability distribution over here. Okay, 0, 1, and 2. We said the probability that you flip heads 0 times is 1/4. Probability you flip heads once is 2/4. And the probability you flip heads twice is 1/4. Right? We saw that on page 1. So if you need a refresher as to like what the logic behind all that was, take a look back at the first example we looked at. Right? It's the it's the same scenario, right? So here's the probability model. So now, if I want to compute the expected value of x, I would say, well, it's possible that x could be 0. The probability x is 0 is 1/4. So there's one possibility. Another possibility is, and by the way, I'm using square brackets here. I just did that to distinguish between the rounded parentheses here and then the square brackets there. You don't have to use square brackets at all. Anyway, they don't do anything mathematically. I'm just using them to show you that this is one possibility. Another possibility is that x is 1, and the corresponding probability is 2/4. And then the last possibility is that x is 2, and the corresponding probability for that is 1/4 again, right? So those are our three possibilities in this case. Now, if you work out the math, 0 times 1/4 is 0. 1 times 2/4 is 2/4. 2 times 1/4 is 2/4. And if you add that up, you get 4/4, which is equal to 1. Sure enough, right? Right? So, so that's the idea, right? This is the formula that we're going to use for less obvious examples, okay? All right. So here's one. It says the number of people living in 10 households in a tiny community is 2, 4, 6, 6, 4, 4, 2, 3, 5, and 5. Let x be the number of people living in a household. Okay, so someone went out to this tiny community that only has 10 households in it. They knocked on every household and asked them, how many people live here? And these are their responses, right? One of the households says, oh, there's only 2 of us. And a couple of the households said, yeah, 6 of us live here, and so forth, right? Maybe this was a census taker or something, right? But anyway, part A says construct a probability distribution for the data. Okay, so a probability distribution is going to list off the possible values of x together with the probability that x takes on that value. I might not have enough room to fit it, to cram it all in here, but I'll try. So looking at the data here, it looks like the smallest answer was 2. So x can't be 0 or 1, right? None of the households said 0 or 1. I mean, how could you even have a conversation with somebody if nobody lived in the household, right? Anyway, but yeah, so smallest x can be is 2. X could be 3, 4, 5, 6, and then it can't be any bigger than 6. I don't see anything bigger than 6. I'm going to say 2, 3, 4, 5, and 6 are the possible values of x. Now, what's the probability that x takes on each of those values? Well, the probability that x is 2, that happened twice, right? Once there and once there, out of 10 households. So probability x is 2 is 2 out of 10. Probability x is 3, or yeah, x is 3, that would be 1. That only happened once, so say 1 out of 10. Probability x is 4, 1, 2, 3 out of 10. Probability x is 5, 2 out of 10. Probability x is 6, 2 out of 10. There's our probability model. If you add those numbers up, they should equal 10 out of 10, right? 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's that. Now, part B says compute the expected value. The expected value is going to be the sum. It's going to be the sum of all the x times p of x's. So I'm going to take turns multiplying this times that, 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 and then I'm going to add them up. Okay, so I'm going to do so it's 2 times 2/10 plus 3 times 1/10 plus 4 times 3/10, and so forth. Okay, 4/10 plus 3/10 plus 12/10 plus 10/10 plus 12/10. And if we add those up, what's that? 24, 34, 37, 41. So there's the expected value, right? 4.1, which is kind of a strange, it's kind of a strange answer. It's like, you know, because what we're saying is that if you were to randomly select a household in this community, how many people would you expect to live in that household? And we're saying 4.1 people. Well, that doesn't make a lot of sense, right? You can't have 0.1 people in a household. So really what we would say is, if you randomly selected one household, then you would expect 4 people to live in that household. But if you randomly selected 10 households, then in those 10 random selections, you would expect to encounter 41 people in total, right? Because 4.1 times 10 is 41. If you randomly, I mean, the community only has 10 households in it, but just imagine, like, if you selected a household and then you did some sampling with repetition, so you were allowed to repeat households. And so let's say that you went out and you randomly selected 100 households. Then out of your 100 selections, you would expect 410 to encounter 410 people, right? 4.1 times 100 is 410, and so forth. So we'll talk about that again a little bit later on, but that's how we interpret this expected value. But what I want to point out now is that this expected value is exactly equivalent to something that we've already seen before. And what it's equivalent to is the mean, right? If we were to compute the mean of this data, we would have said, well, it's 2 plus 4 plus 6 plus 6 plus 4 plus 4 plus 2 plus 3 plus 5 plus 5 divided by 10, right? And if you squinted it hard enough, you'll see that this is exactly the same as that. I mean, for one thing, like, you could do the addition and you're going to get 41 out of 10. But for another thing, to see why it's equivalent to like 4 out of 10. So here we have 2 out of 10 plus 2 out of 10. And those two things combine to give you 4 out of 10, right? Here we have a 3 out of 10. That's where that one comes from. The 12 out of 10 comes from the fact that you've got 4 out of 10 plus 4 out of 10 plus 4 out of 10. That gives you 12 out of 10, right? Anyway, but this is just another way to do the exact same calculation. So, and this is true in general. So, oh, you probably couldn't see what I was just pointing at. Oh, you know, this .chem only shows such a small portion of the page. Oftentimes I find that I'm pointing to things you can't see. But the moral of the story is that this is just a different way to do this same calculation. And you might wonder, like, well, if we had this formula already, right? This is the formula we used in chapter 3, then why did we need to introduce this new formula? And the answer to that is that we can't always use this old formula. There are going to be situations where we can't use it, and so we have to rely on the expected value instead. The other thing is that it gives us this different interpretation that we've been talking about, right? It gives us this other interpretation for what the mean really is. The mean is what we would expect to occur, right? Anyway, this is just saying what we said before, right? The mean is the same as the expected value. Here I'm using a little subscript of x on mu, right? I'm saying mu sub x. I use that notation. Your book uses this notation as well, but I use this notation only to distinguish between things that are going to happen later on in chapters in chapter 8, really. So in chapter 8. So I'm just using a subscript of X to distinguish between stuff we'll talk about in chapter 8. Okay. Anyway, again, kind of just changing our perspective a little bit. We talked about the law of large numbers in chapter 5. What the law of large numbers says about the expected value is that the more experiments we run, the closer our sample mean is going to get to our expected value. And that's an important thing. It's like the expected value, when we compute the thing this way, it's going to give us the population mean. Whereas when we, well, yeah, if we just go out and collect a sample, then we're only getting a sample mean. But what the law of large numbers says is that the more experiments we run, the closer our sample mean will get to our theoretical mean, to our expected value. Okay. So, so we can re-express the mean in terms of expected values. We can do the same thing with standard deviation. So for standard deviation, the way that we calculate that using expected values is that the standard deviation is the expected value of x squared minus the mean squared. The expected value of x squared, we calculate that by doing the sum of all the x squareds times p of x's. Okay. I'll give you an example of this because I know it's maybe a little bit confusing at first, but it'll become less confusing to you if we look at an example. So here's an example that says, suppose we ask a basketball player to shoot 2 free throws. We record whether she makes 0, 1, or 2 of the free throws. She takes a break, and then we repeat the experiment. After repeating the experiment several times, we end up with the following probability distribution. And here, x is supposed to represent, x is supposed to represent the number of shots made. So, sometimes she made none of the shots, right? She shot 2 free throws and she missed both times. That only happens to her 1% of the time. Sometimes she just made one of the shots. That happened 28% of the time. But most of the time she made both shots, right? 71% of the time, which is good. If it were me shooting the free throws, these things would be reversed. But anyway, so this is the probability distribution. Now, in part A, it says find the mean, right? Find mu sub x, find the mean. And if you think about trying to use the formulas that we came up with back in chapter 3, way back in chapter 3, you'll notice that we can't do it. We can't find the mean using the formula that we came up with in chapter 3 because we don't have all of the data in front of us. What we have is a probability distribution. So we have to rely on the expected value formula that we talked about in this section. So this is one of these examples where we have to use the expected value in order to find the mean, right? So we're going to say, well, I can calculate the mean by calculating the expected value. The expected value, in this case, it's going to be this times that, plus this times that, plus this times that. So it's going to be 0 times 0.01 plus 1 times 0.28 plus 2 times 0.71. So let's see, 2 times 0.71 plus 0.28, and that comes out to 1.7. Okay, so there's the expected value. So let's talk about interpreting this a little bit. What we're saying is that if this particular basketball player stands up to shoot 2 free throws, we expect her to make 1.7 of them. Well, not really. What we would say is that if we do this experiment once, so she shoots 2 free throws, we expect her to make both of them, right? Because you round this to the nearest whole number and you get 2. But if we repeat the experiment 10 times, so in other words, each trial of the experiment consists of 2 free throws, right? So if we repeat the experiment 10 times, then in total she's going to shoot 20 free throws. we would expect her to make 17 of them, right? Because 10 times 1.7 is 17. If we repeated the experiment 100 times, we would expect her to make 170 of the free throws, because 100 times 1.7 is 170. If we repeated the experiment, I don't know, 250 times. If we repeated the experiment 250 times, 250 times 1.7 is 425. So if we repeated the experiment 250 times, we would expect her to make 425 free throws in total. Okay, so that's how expected values work. Okay. But if we only repeat the experiment once, then we say we expect her to make 2 free throws, right? So that's the expected value. That's also the mean. Okay. Now let's find the standard deviation. Okay, so standard deviation. Here's the formula that we're going to use for standard deviation. Okay. We already have the mean. We just finished computing that in part A. So what we need to focus our attention on is computing this thing. So let's compute this piece of the formula, and then we'll plug it in. Okay. So let's compute e of x squared. E of x squared is the sum of all the x squareds times p of x. So it's going to be exactly what I wrote down before for e of x, only I'm going to square these numbers. I'm not going to square the probabilities, okay? I'm just going to square the values of x. So it's going to be 0 squared times 0.01 plus 1 squared times 0.28 plus 2 squared times 0.71. And if you add those things up, you get 3.12. Okay. Now that's not the standard deviation, that's just the expected value of x squared, right? The standard deviation is the square root of the expected value of x squared minus the mean squared. So let's get the standard deviation. Okay, so let's see. So this is going to be the square root of 3.12 minus the mean squared. Okay, we're not squaring the 3.12. 3.12 is e of x squared. So we're just replacing e of x squared with 3.12, right? Because e of x squared is equal to 3.12. We do need to square the mean though, because 1.7 is just the mean, right? And we want the mean squared, so we put in the mean squared. Okay, and now you punch this into your calculator. When you do, be sure to use correct order of operations, right? Square the 1.7 first, then subtract it from 3.12, and then take the square root. Don't do 3.12 minus 1.7 and then square. You're going to get the wrong answer. You have to do exponents first. Okay, let's see what we get. Oh, my kids are just yelling at each other. Such turmoil, probably over some toy or something. Anyway, so that's that, and then you take the square root of that, and you get about, this is approximately 0.4, oh, how many decimal places? Let's go 2 decimal places. Let's say 0.48. Okay, so there's the standard deviation. You should appreciate this, I think, because when we did standard deviations by hand in chapter 3, it was a kind of a long and tedious process. This is a lot easier. Okay, so that's that. As we've already discussed, the new formulas that we've learned about in this section give us a way to compute the theoretical, or in other words, the population mean and standard deviation, just based on classical probability, right? You don't have to rely on experimentation at all, which is really pretty nice. And it turns out to be very useful especially in the next section. For now, let's look at a couple of applications. I think this first application is kind of silly, but the second application is really pretty good. But let's talk about them. And I'll tell you this, in math class, typically the easier the example, the less realistic it is. The harder it is, the more realistic it is. And so number 7 is a little bit more challenging to wrap your brain around, but it's a better example of, it's a better reflection of reality. Anyway, but number 6 says, a bank vice president feels that each savings account customer has on average 3 credit cards. The following distribution represents the number of credit cards people own. Okay. So 27% of people had 2 credit cards, and 3% of people had 4, and so forth. Is the vice president correct? Well, to see if the vice president's, I mean, it's pretty obvious that he's not, I think, right? The vice president thinks, this particular vice president thinks that his customers have 3 credit cards on average, but only 8% of his customers did. I would say the average number of credit cards is probably somewhere between 1 and 2. Anyway, so how do we see if the vice president is correct? Well, we have to compute the average. We have to see what the average is. Only we can't compute the average using the methods from chapter 3 because we don't have all the raw data. Only expected value. Right? How many credit cards would we expect one of these customers to have? Right? So the expected value would be 0 times 0.18 plus 1 times 0.44 plus 2 times 0.27 and so forth. Okay. And then we punch that into our calculator. So I'm going to do 0.44 plus 2 times 0.27 plus 3 times 0.08 plus 4 times 0.03, get 1.34. So is the vice president correct? No, he's way off. It's kind of crazy. How could the vice president have such an incorrect assumption about his customers? If he's the vice president, he should be a little sharper than that, don't you think? Anyway, but no, he's wrong for sure. Okay, so that's that one. Number 7. A term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Actually, I think they're usually paid monthly. But anyway, suppose a life insurance company sells a $250,000 one-year term life insurance policy to an 18-year-old male for $350 per year. The 18-year-old male is a sucker. If you're 18 years old, you don't need a $250,000 life insurance policy. I mean, I guess unless you happen to have like a wife and kids at that point, which is unlikely. But yeah, the reason you get life insurance is so that, first of all, you can pay to bury yourself. But then second of all, so that your dependents have some money to live off of while they are trying to get back on their feet, right? So like in my case, it makes sense to have a $250,000 life insurance policy because I have a wife and 3 children and they rely on my income. So if I die, they need, they need some money while they're trying to figure stuff out. But if you're 18 years old, man, you don't need $250,000. Like $20,000 is plenty. 20,000 should be more than enough to get a burial plot and a headstone, So anyway, but moving on. It says, according to the National Vital Statistics report, the probability that the man will survive the year is 0.998937. Compute the annual expected value of this policy to the insurance company. So we're looking at this through the perspective of the insurance company, not through the perspective of the 18-year-old. Okay, so we want to know what's the value of this policy to the insurance company. Well, there are only two possibilities here. Either the 18-year-old survives or the 18-year-old dies, right? So what we'll do is we'll say let X be the amount of money the insurance company makes. The insurance company makes. Okay, so X is the amount of money the insurance company makes. Now, it's possible that X could be $350. This happens if the 18-year-old survives the year, right? So this happens if he survives. If he survives, then the insurance company makes $350. What's the probability that he survives? Well, it tells us the probability that the man will survive is 0.998937. Okay, so the probability that X equals 350 is 0.998937. But it's also possible that this 18-year-old could die. It's not very likely, but it's possible, right? If the 18-year-old dies, then the insurance company has to pay $250,000 to his beneficiary. Now, they don't quite lose $250,000 because the 18-year-old paid $350 for the life insurance. So really, they lose $250,000 minus 350. So really they only lose $249,650. But that's how much they have to pay. Well, this is how much they have to pay out to the beneficiary. This is how much they lose, right? Because this is how much the 18-year-old paid for the policy, right? But this is how much the insurance company loses. So it's possible X could be negative 249,650. Okay, this is if the 18-year-old dies. So if the 18-year-old survives, then they make $350. If the 18-year-old dies, then they make negative $249,650 because they have to pay $250,000 to the beneficiary. Now, what's the probability that this happens? What's the probability the 18-year-old dies? Well, if there's a 0.998937 chance that he lives, then there's a 1 minus 0.998937 chance that he dies. So 0.101063. Okay. So now we can compute the expected value, right? It says compute the annual expected value of the policy to the insurance company. We can say, well, the expected value is going to be X times P of X plus X times P of X. And then we plug that into our calculator. 350 times 0.998937 plus negative 249,650 times 0.001063 is 84.25. Okay, so there you go. That's the amount of money that the insurance company expects to make. Well, that's not quite true, right? Really, the amount of money the insurance company expects to make is $350 because that's the much more likely scenario. But on average, if the insurance company sells this policy to a bunch of 18-year-olds, then on average they can count on making $84.25 for each policy that they sell. So that's that one. And here's your homework assignment from 6.1.